Hello, this is section 2.5, which is about continuity. So here we're going to discuss we have two definitions of a function being continuous. So the first definition is that a function y equals f of x is continuous at x equals a if the limit of f of x as x approaches a equals f of a. So if the function is not continuous at x equals a, we say that the function is discontinuous at x equals a. This is the first definition is about one statement function. This y equals f of x. Is this function continuous at x equals a? If this is satisfied, limit on the left side you have the limit of f of x as x approaches a. On the right side of this equation, you have f of a. So if the two sides are equals, then we say the function is continuous at x equals a. For example, we're looking at the function y equals x squared, and at a equals 2. Is this function continuous at a equals 2? So we check. F of 2 equals 4. Okay, so that's the right side of the equation here. We find f of 2. Since a is 2, so f of 2 is 2 squared, which is 4. Now we go to the left side. We take the limit of the function as x approaches 2. So this is so we take the limit of the function, which is x squared, as x approaches 2. Since the x squared is a nice function near 2, we can just plug in x equals 2 to get 4. So basically, statement 1 and statement 2 are equal. So that means the limit as x squared as x approaches 2 equals f of 2, because on the left side, we're getting the result to be 4. On the right side, we get 4 also. So 4 equals 4. So we say that the function f of x equals x squared is continuous at x equals 2. So we go to another example. For instance, we look at this function. Okay, this is a piecewise function. So we can see from negative infinity to 3, the function is a straight line. From 3 to infinity, the function is a parabola, some type of curve, right? So the question is this function continuous at a equals 3? Since we have a piecewise function, it's a function that is given in two pieces, two graphs. So you have the first graph and the second graph. We call this a piecewise function. So anytime you're dealing with a function that is piecewise, to know whether the function is continuous at a given point or not is to use the second definition. So the second definition of a function being continuous is about piecewise function. So we say a piecewise function y equals f of x is continuous at x equals a if the first condition is that the function evaluated at a must be defined. So f of a must be a number. It must not be infinity or negative infinity undefined. Second condition, the limit of f of x as x approaches a must exist. The limits must be a finite number. 3. 1 and 2 must be equal, meaning f of a must be equal to the limit of f of x as x approaches a. So only then, when the three conditions are satisfied, then we say the piecewise function is continuous at x equals a. For example, we go back to our function that we gave earlier. Is the piecewise function continuous or discontinuous at x equals 3? So the function is nice from negative infinity up to 3. And then from 3 to infinity, we have a curve, which is a nice, smooth. So the function has no problem except when x equals 3. So we have to check at this point x equals 3. So we call it a equals 3. So we verify the three conditions. What is f of 3 equals to? So we look at 3. wherever we have a closed circle, that is f of 3. Okay, so f of 3 equals 2. 2 is a finite number. So that means f of 3, which is 2, is defined. So the first condition is satisfied. We go to the second condition. We take the limit of the function f of x as x approaches 3. Because when we say that the limit as x approaches 3, we will approach 3 from both sides. Okay, from the left side and then from the right side. So when we approach 3 from the left side, we have then this function here. When we approach 3 from the right side, we have this function. Okay, so we can then talk about the left limit and the right limit. So we can divide, we can kind of split this limit as x approaches 3 in terms of two limits. This is what we call the left-hand limit. So x will approach 3 from the left side of 3. And then here, x approaches 3 from the right. So we look, as x approaches 3 from the left, this curve is approaching this open circle. This open circle is at 5, y equals 5. So we say the limit as x approaches 3 from the left of the function f of x is 5. Then we approach 3 from the right side. As we come in closer and closer to 3 from the right, if we move to the graph, it's going to hit this graph. And this graph is approaching to this closed circle. The closed circle is at y equals 2. So we say the limit of f of x as x approaches 3 plus equals 2. Then, in conclusion, we can say the limit of f of x as x approaches 3 does not exist because we're getting two different answers. 5 and 2. 5 is different from 2. So we say the limit of f of x as x approaches 3 does not exist. So this condition, this second condition of the piecewise function is not satisfied. So we stop here and we say the function is discontinuous at x equals 3. So we go to another example. We have the function f of x equals 1 over x plus 2, and they give us a to be negative 2. So why is the function discontinuous at a? So the question is, why this function discontinuous at a equals negative 2? If you plug in negative 2 for x into the function, you get 1 over negative 2 plus 2, which is 1 over 0, which is undefined. So undefined means not defined. So clearly the function is, because the first condition, f of negative 2 is not defined, we say the function is discontinuous at a equals negative 1, because the first condition is not satisfied. So then we go to a different example. Now this time we're dealing with a piecewise function. So f of x equals 1 over x plus 2 when x is not negative 2. And the function f of x is exactly 1 when f is exactly equals to negative 2. Is this function continuous at a equals negative 2? So that's a question. So since it's a piecewise function, we have three conditions to verify. The first condition is f of negative 2. Is this defined? Well, it says when x is negative 2, the function is 1. So f of negative 2 is 1. 1 is a finite number, so that means this condition, this f of negative 2 is defined. So the first condition is satisfied. We go to the second condition. We take the limit as x approaches a of f of x, and it must exist. So the limit as x approaches negative 2 of 1 over x plus 2 equals 2. So again, since this is a piecewise function, we can split this. Okay, so when x approaches negative 2 from the left, okay, the function is approaching negative infinity. When x approaches negative 2 from the right, the function is approaching infinity. So how did we know that? Okay, so when you have a negative 2 here, x approaches negative 2 from the left, so you pick a number that is to the left of negative 2, like, and then close to negative 2, like negative 2.001. When you plug this into the function here, so you get 1 over negative 2.001 plus 2, which gives you 1 over negative 0.001, which basically is negative large, which is negative infinity. Now, when x approaches negative 2 plus, it means we at negative 2, but to the right side of negative 2, yet close to negative 2. So we pick a number to the right of negative 2, but close to negative 2. An example is negative 1.999. We evaluate the function at that number. We get 1 over negative 1.99 plus 2, which gives us 0.001. So 1 divided by 0.001 gives us a large positive number, so which the translation is infinity. So because we're getting two answers, one is negative infinity, another one is infinity, and those are not finite answer. So the second condition is not satisfied. So we say this limit as x approaches negative 2 of 1 over x plus 2 does not exist. So hence the second condition is not satisfied. So the conclusion is the function is discontinuous at a equals negative 2. And we have our last example. So the last example is that f of x is it's a piecewise function again. So f of x is x plus 3 when x is less than equals negative 1. And the function f of x is a 2 to the x when x is greater than negative 1. And we want to verify if this function is continuous or not at a equals negative 1. So we need to find f of a. So what is f of a? Because we have an equal sign here, x equals negative 1, so we're going to evaluate this x plus 1 at x equals negative 1, which will give us negative 1 plus 3, which is 2. Since 2 is finite, we say the first condition is satisfied. So we go to the second condition. We're going to take the limit of the function as x approaches negative 1. Because we have two different functions, we will take the limit as x approaches negative 1 from the left, which is this one, and then from the right, which is 2 to the x. So x approaches negative 1 from the left, we use x plus 3, which we plug in negative 1 for x, we get 2. When x approaches negative 1 from the right, we're going to take the limit of 2 to the x. And as we plug in negative 1 for x, we get 2 raised to negative 1, which is a 1 over 2. So we say the limit as x approaches negative 1 of f of x does not exist, because as x approaches negative 1, we're getting two different limits, 2 and 1/2. So that means the limit does not exist. So the second condition is not satisfied. Again, we say the function is discontinuous at a equals negative 1. Thank you.